In this video, I introduce a deep conservative policy iteration for policy improvement. Reinforcement learning is framed as a Markov decision process with a tuple SAPR gamma, where S is a state space, A is an action space, P is a Markovian transition probability, R is a real-world function, and gamma is discount factor. An RL agent uses a stochastic policy pi to find the action A in a state S and receives the expected real-world R pi, and then moves to next state S prime via the transition probability P pi. The state function V pi and the state action function Q pi of a policy pi are defined as here, this V pi and this Q pi explained in this figure. If S0 sampled from an initial state distribution mu, a new policy pi k plus 1 at iteration k is updated using this formulation, where selection of pi k plus 1 makes q pi k maximum that is computed with the state sampled from mu. Conservative policy iteration uses a mixture coefficient alpha k to compute a stochastic mixture of all the previous graded policies, as shown here. Considering the error between q key and his approximation q pi key to be epsilon key, temporal difference applied to the CPI update leads to the following iterations. This for q key and this for pi q plus 1 explained in this figure. Deep conservative policy iteration uses two neural networks, q theta and pi w, to model the state action function q key and the policy pi key. Two respective target networks, q bar and pi bar, are defined to evaluate the state action function and the policy. The transitions SAR, S prime are sampled from environment during training and stored in a forced in and forced out replay buffer B. The evaluation step consists of a regression problem to minimize the quadratic error between q theta and the approximation of t and q bar. The regression loss over a finite set is defined as here. This target and this prediction explained in this figure, whereas the empirical average is computed on all transitions SAR, S prime. The improvement state approximates a distribution over actions for each state. A loss function error pi is used to minimize the expected value function over the state of expected k error divergence between the online policy network and the stochastic mixture as shown here. This target, this prediction as shown in this figure. Error Q and error pi are minimized with a fixed number of steps of batch SGD, and the target networks update online. Each grading step is performed after a fixed number of transitions are collected from environment. The samples for evaluating pi w originate independently from older policies. During training, DCPI samples transitions with pi w epsilon, the policy which chooses a random action uniformly of A with probability epsilon and follows pi w with probability 1 minus epsilon. The pseudocode of DCPI method as shown here. DCPI uses adaptive mixture rate alpha in his update to guarantee improvement of the policy, whereas the policy pi tilde is a greedy policy with respect to q pi. And the advantage a pi mu pi tilde of greedy policy pi tilde is over previous policy pi as shown here. And R is a maximum possible reward. DCPI estimate A pi mu pi tilde over batch B at step K. A pi tilde is approximated with AK tilde caret. A pi mu pi tilde is approximated with AK caret as shown here. The term R over 1 minor gamma is approximated by the estimate Q key caret. The efficient 1 over 4 is replaced by a hyperparameter alpha 0. The moving average MK and the moving maximum QK plus are used to compute the adaptive mixture rate as shown here. This is the mixture rate alpha. For more details, please check with these references. Thank you. Bye.